Hi everyone, I'm Jian Gong from Central South University. Today I'm going to share our latest research, robust inertial motion tracking through deep sensor fusion across smart earbuds and smartphones. Inertial sensors, IMUs, including gyroscope, accelerometer, and magnetometer, have been a standard module in modern mobile devices and play a fundamental role in many ubiquitous computing applications. Example use cases include tracking users' trajectory in VR gaming, navigating a user in GPS-denied indoor navigation, serving as a low-power fitness tracker, complementing GPS in last-mile scenarios. The underlying algorithms, often referred to as inertial odometry or data reckoning, aim to estimate the moving direction and distance of the user relative to the Earth's coordinates, the global reference frame. Unfortunately, to track human mobility with on-body IMUs, the sensor readings are intrinsically noisy. The motion noise are generated unconsciously and inevitably, either by limb swinging, shaking during normal walking, or by ordinary maneuvers such as phone rotation or moving into pocket. Such motion artifacts are indistinguishable from walking-induced IMU dynamics, and the resulting error will be further magnified by gyroscope and accelerometer integration, resulting in exponential error propagation over a walking trajectory. In other words, it is irregular motion artifact itself that plagues inertial motion tracking in practice. In this paper, we propose Deep Inertial Tracking (DeepIT), a deep learning-based sensor fusion framework to enable truly robust inertial motion tracking in the wild. Our key insight is simple: to combat the motion noise, we need to incorporate additional IMU sensors whose measurements are not likely to be contaminated, at least not simultaneously with the smartphone's IMU measurements. We realize such sensing diversity using smart earbuds, which are emerging as a new generation of wearable devices. In many of the desired use cases of inertial tracking, such as indoor navigation and outdoor run tracker, the earbuds are accompanied by the user's smartphone. Smart earbuds are far less susceptible to motion pollution than handheld smartphones because head rotation occurs much less frequently and at a much smaller scale compared with the body limbs. Our DeepIT model segments the input IMU sequences into small windows and outputs the polar coordinate representation of the user's location. To effectively harness the complementary capability of the smartphone and earbuds, we design a reliability network which gauges the confidence of sensing from each IMU. Which IMU is suffering less from motion artifacts momentarily. The reliability network then forwards its output to an attention module, which fuses the two IMU's recordings based on their reliability. Observing that the IMU data is a continuous stream of samples and motion artifacts, despite burstiness, do exhibit short-term correlation. Therefore, we cast the reliability network design as a sequence learning problem and construct it based on the LSTM model. Even with sensor fusion, the angular and radial components of localization are still susceptible to cumulative error caused by the summation of each window's offset, whereas the drift of radial components cannot be compensated by additional measurements. The angular counterpart can be calibrated by magnetometer reading, which is not susceptible to cumulative error. The noise level of both IMUs, represented by reliability vector, is adopted as a metric to determine how much the magnetometer reading of the phone's IMU can be relied on. Based on the value of reliability vector, the magnetometer reading is then fused with angular component determined by the neural network for a more accurate angular offset estimation. There is no public dataset for inertial tracking using both smartphone and earbuds simultaneously. Therefore, we collect our own dataset with pedestrians carrying Android phones and wearing smart earbuds. We use the eSense, an experimental smart earbuds device developed by Nokia, which can stream gyroscope and accelerometer readings through BLE through an associated smartphone. Our dataset covers a comprehensive set of real-world usage settings. To examine the performance of earbuds and benchmark solutions under different levels of motion noise, the dataset incorporates four types of walking patterns: normal walking, walking while swinging phone occasionally, walking while swinging phones and moving heads alternatively, walking while moving heads occasionally. In NW scenario, you can see that the reliability of the phone is always higher than the earbud. This is because the phone endures clearer periodic walking patterns than the earbud, so its translation estimation is more accurate. In RP scenario, the earbud's reliability is always higher than the phone. This matches our expectation because the phone endures more motion noise in this scenario. In RPE scenario, the two sensors' reliability level change alternatively. Comparing with the original IMU data within the same time frame in Figure 6, we find that the lower reliability period precisely corresponds to the moment when the sensor induced motion noise. This indicates that our reliability-aware attention scheme faithfully tracks the motion noise intensity and adjusts the fusion weights accurately. Due to the time limitation, we only reduced the high-level ideas of our research. For more details, please refer to our paper, Robust Inertial Motion Tracking through Deep Sample Fusion across smart earbuds and smartphones.